begin. And I guess Jorg is going to tell you what this is.
No? Yeah, it's clear. You can watch it tonight, so after the issue. Yeah. Oh, you know, there's a small comment. If it's very clear, you can see it with your naked eye.
So you took it last night.
Oh, wow.
Yeah. Beautiful.
After I went home drinking, after the drinking when I went home, it was clear that took 15 minutes before I went home.
How long was the exposure to get that photo?
This was 10 times 30 seconds.
Do you have a tripod?
Yeah.
Otherwise, you have really still hands.
No, you have a small tracker in the track space.
What time of the night did you take this?
What?
What time? Last night?
At midnight or something. You basically have to see it before the moon comes up, then it would be much better.
Oh.
So the moon comes up at 10 at night or something.
Only one tail or two?
I don't know. It's not, it was very bright yesterday, so it was lots of light from the moon, so it was and you still see the fog from the clouds. You still see the clouds.
Now we have to send a probe there.
No. Okay, guys. The last section of my talk about this habit of connecting the quantum worlds and things together. Today, I want to focus a little bit of connecting to superconducting circuits and spins. And first of all, I want to warn you, I'm not an expert in superconducting circuits. So there are many, many more experts who can show that in all the details of how these superconducting circuits work. They're just a fantastic tool. They're absolutely fantastic. The things you can do stuff which people who in quantum optics dreamed of and thought they will never be able to do within 100 years, and you know, people were able to do that within whatever 5 years of the first circuit experiment. Just as an example, you know, the basic thing what you always have is in these circuits is you have some kind of a superconducting qubit. This is Josephson junction somewhere in the middle here, and a large capacitor which couples to a microwave resonator, which is a strip light resonator. Or you have various other types of theory, other type of qubit and also resonators. To do that, and you can get the coupling between a microwave, these qubits, and the microwave resonator is very strong. This was the very first experiment when they did it from Rob Sharkov's group. And I still remember that just when they did this experiment, I was visiting guys at Caltech, Kimball and Hideo Mabuchi. And Hideo just came back from a conference where Steve Gerwin was saying, talking about, you know, the first time talking about that they can do this with these resonators. And he came back and said, you know, we are all out of business. In fact, you know, he would probably, and now, if you would take a model plot with the same resolution, these two things would be probably separated by hundreds of parameters. So the coupling is, you can make extremely strong couplings in very, very narrow resonances. And you can, for example, create, you know, arbitrary superposition state. This is 0 plus 1, or 0 plus 2, 0 plus 3, 0 plus 4, 0 plus 5. And this is a measurement of the Wigner function. That's a calculation of the Wigner function. That's from John Martinez' group. And you can do these things up to 10, 15 photons. And you can measure every single photon on there with this, you count them, but you cannot measure 2 or 3. You have to count them one by one. And so you can do lots and lots of stuff. It's an incredible, you know, technology tool. Now, if you want to read a little bit of how to connect these things to superconductors, there's a nice review which came out last year from the guys in Japan, from the risky guys from around Franco Nori. And so he basically goes through many of these things in a very much more detail than I can go over here. The basic idea behind there, how to make a qubit, is to say that, you know, an electronic resonant circuit you describe as a harmonic oscillator, but that would be really bad because an harmonic oscillator, you cannot have a good qubit, because if you start to drive it, you excite coherent states as you have in optics. So what you have to do, you have to put in some nonlinearity. This nonlinearity is Josephson junctions. And then you have to just to be electrical engineer, very clever, to make various types of circuits, and you can use the charge as a qubit, you can use the flux as a qubit, you can use the phase of the oscillator as a qubit, and you can do them with very high impedance or low impedance, and various types of tricks. And it was amazing. I think the first time that somebody made an oscillator like this and showed that you can have two states and make a transition and drive this transition, the lifetime was something like a few nanoseconds. But now the lifetime is, I think, is approaching 100, is way over 100 microseconds. So the thing became, within, that's probably, something like a little bit more than 10 years, you gained 6 orders of magnitude in coherence time in this type of circuits. And so you have now, I think you have now devices which are very, very close in the ratio between coherence to operation time, which the ion traps are. But you basically build them in a circuit. So it's a fantastic way, and behind each of those various of these qubits, there's a huge literature behind there, a huge history behind there to do that. Now, the ways how to connect these things are cavities. And we know this, we have heard much about the regular optical cavities, and what is nice in these circuits, if you take a transmission line, which is basically a single conductor with 2 ground plates, then you match them correctly, that you have the 50 ohm impedance, and if you make a gap between there, this is small capacitor, you can make this, depending how big this capacitor is, you create a resonator in there, and these resonators can have very, very high Qs, up to 10 to the 7 by now, 10 to the 6, 10 to the 7, and they're very easy to be done, and I will show you the beautiful thing in there is that the volume of this resonance is much smaller than lambda cube. So you get very strong enhancement of the fields, even for a single photon. Now the idea was to take these resonators, and these resonators are now the ones that wire up together these qubits, so you can have qubits that couple to the electric field, yeah, like a charged qubit would couple to. So a resonator like this, it has a strong electric field here and a strong magnetic field here. A strong electric field here again, a strong magnetic field here again, a strong electric field here again. So if you put something that you want to couple to the electric field of the resonator, you put it there where you have the maximum of the electric field. If you have something like coupling to a spin or the magnetic moment, you have to put it there where you have lots of magnetic field. So if you take a charged qubit, you would couple it to the maximum of the electric field. If you take a flux qubit, you make a resonator who has, it's just a resonator which would have the maximum magnetic field here because it has the strongest current here. Yeah? And the phase qubit, you basically couple to the phase of the wave of the thing that comes out here. So you can play around and make this type of circuits, and I think one of the key parts in understanding what is happening comes out of, I think it's Jorg Schmiedmayer and Steve Gervin's groups at Yale, and there's a beautiful long article by Blair et al. in Physics A 2004, which basically lays out what's something like 10 years ago. So this thing came out something like 10 years ago, and it basically makes the connection between what you have in regular cavity QED to the thing that you have in the circuit QED. How you describe a resonator like this as an electronic circuit, and how to relate that to what we know from cavity QED. Now, as I said before, what makes the circuit QED so extremely powerful is that the dipole moment of these qubits is usually very large, something like 10,000 times as large as a hydrogen atom. So you can get a very strong coupling even to a very small field. Nevertheless, the field of a single photon on this resonator is very, very large because its volume is extremely small. This volume is basically the length times the distance, this distance here squared, and so that typically you have tens of gigahertz, so you have something like a few centimeter wavelength here, and if a few microns here, you see that compared to lambda cubed, you have 10 to the 6 lambda cubed. This is that gives you a very, very large field compared to what you would otherwise expect from a microwave photon. So that typically it's interactions you have between the circuits, within the circuits, 10 to the 3 to 10 to the 6 is large than with real atoms. And that makes it why these things are so powerful. The next question is then, can you couple other things to it? And so I will tell you a little bit about coupling trapped atoms to it. That's how I got into that. But the first time I heard about these things, I thought about, cool, you should be able to couple atoms to this directly. Of course, there's atoms coupled through the spin, so you can take the same thing as an impurity spin, coupling two atoms. You can take a quantum dot, like some electron spin in another wire, or you can electricity created quantum dots. And there is a huge literature out there, and for the moment, and basically, more or less, most of the systems you can think of were coupled to this microwave, to the microwave resonators. So in that sense, just going back to the diagram I had in the beginning of my first talk, where I said, okay, there's all these many different systems. So microwave cavities are a key element, I think, where you can really will be able to hybridize and couple these systems together. And we have heard, much of that also to the nanomechanics, which I deliberately didn't put on there because there's so many other talks about this nanomechanics. And I will not mention anything about the nanomechanics because I don't do it. So, how can I make now an interface between the microwave and the spin? As we said, we have to go and look more carefully at that resonator. Let's put in numbers. And if you take a resonator like that, what's a typical coupling strength you get to a cube per pair box atom, which would be some superconducting qubit, you would get about, typically in order of magnitude, 100 megahertz coupling. If you take a Rydberg atom, which can have a very strong electric dipole moment, and put it 50 microns away somewhere here, you get a coupling of about 100 kilohertz. If you take a polar molecule and put it a few microns away, you get a coupling of 10 kilohertz. If you put an electron spin there, you get a coupling of about 100 hertz. Now, if you have a resonator which has, say, a few gigahertz and a Q of something like 10 to the 6, 10 to the 5 to 10 to the 6, so you basically have a line width which is in the 10 kilohertz range. So you see that if you want to couple single systems, you might be able to couple the upper ones. You cannot. It's very, very difficult to couple the single electron spin. The typical fields that you get, and we look at that a little bit more, like you have something, a single microwave photon will give you a field that's typically a volt per micron. Fields that are volt per meter, even a single microwave photon will give you fields that are volt per meter electric fields, or about 100 microgauss field of a magnetic field. Now these coplanar wave resonators are very nice to work with, but you could in principle go and design your own electric circuit where you take the inductance and the capacitance in specific places and then shape them so you can enhance electric or the magnetic fields that they have, and it allows you to enhance the field strength by something like up to a factor of 3, maybe 10, but then things get to be a little bit more complicated. So let's look in more detail how the field of one of these transmission line cavities look like, and this is you take that field that typically have your ground plate, you have your conductor strip, and you have another ground plate, you have a substrate, and the substrate usually has to be something which has a very, very low loss tangent for that, so it's usually sapphire or something like that. You get this very small mode volume, which is typically in the order of lambda times L times, or it should be W squared. This comes to me. Lambda times W squared, and there's a very strong near field enhancement, which is in this range. Lambda over W should be, if you follow that factor. So you have an enhancement something like a factor of a huge enhancement of the electric field strength, and the volume which the electric field strength goes like this curve of the volume. There's a very long lifetime of the photon in there, which is about 25 microseconds for Q is 10 to the 6. And you can do the complete calculation, and you see that how does the magnetic field look like, and the magnetic field vectors look like, and so you can basically, if you want to couple something very strongly, you have to put it somewhere in there, and you can do that. Now, there were many different proposals, as I showed before. So you can put any type of spin you think of, you just put somewhere in the gap in here, like it could be some nitrogen in the C60 cage, it could be phosphorus and silicon, it could be, the electron spins of an NV center, it can be a rare earth ion, it can be some molecular magnets, it can be electron spins in superfluid helium or whatever you think, and that you put there where there's a maximum magnetic field, or you can put a polar molecule where you have a maximum electric field or something like that. And there were many proposals, and even so that for many of these spins, the single coupling is very weak. If you take 10 to the 10 to 10 to the 12 spins, you can get the megahertz collective coupling in there. Now, yeah?
So I would have guessed that the fields are sort of confined quite strongly to the plane of the resonation, but that didn't seem to be the case in the.
I will show you that. I will show you how they fall off in just next experience here. So the first thing we thought about, if you want to really couple something to spins that live very long, so you want to take an atomic ensemble. If you take an atomic ensemble and you couple a microwave field to this atomic ensemble, you create basically exactly the same collective state that you create by using this optical Raman transition I told you in my last lecture. So this would also give you a very natural way of converting a microwave photon in an optical photon, because you write the microwave photon in this ensemble. In this ensemble, you can read out the spin wave by transferring it in an optical photon. Yeah. Now the question is that can you get enough atoms that sit close to there and hold that? Would that work? So you take now numbers, you calculate for rubidium, this has a 6.8 gigahertz resonator, and now these are only the field directions. We didn't show the vectors, yeah. But if you sit, say, in the middle here, if you sit somewhere here, then you see that the field. What's it? That's how the field folds off in the blue line from how many microgauss field you have going up, and this is how the field would fall off in the center of the system. And this is the line a few micron above this, or 1.5 micron above the surface, where we were able to trap atoms in our atom chip experiments. Then you get a field that looks like that. So you have something like about 40, so typically in the order of 40 microgauss or 50 microgauss field.
Just for a single photon.
It's a single photon field. It's a single photon field. Yeah. So if you take that and it corresponds to about 2 microvolt electrical potential, and it's a field of electric field of 0.7 volts per meter that it would create. In that, with this substrate, and so this was on I think a sapphire substrate calculated. Now we know that we can take neutral atoms in the chips, and we did experiments, so we can bring them down to a micron to the surface. Yeah, and they live there for hundreds of milliseconds. Principle. If you don't get them too dense, so you can basically think about that, which is the maximum density you can get in the trap to hold there, and you have something like 10 to the 6 atoms. You should be able to get 10 to the 6 atoms in a very elongated cloud, sitting there very close somewhere here, in between the gap on this point here, somewhere where you can trap them. Now, what would you see if you take that? So would now make a spectroscopy of that, you would see a vacuum Rabi splitting like that for about 10 to the 6 atoms, and about 10 to the 5 atoms you would see a vacuum Rabi splitting like that. And if you measure the phase of the transmitted part, you would see this type of thing. So having something like 10 to the 5 to 10 to the 6 atoms sitting there would allow you to get into the strong coupling machine for cavity QED, including this with this due to the collective coupling. That's in principle So it is in principle possible, but experimentally, it's a nightmare. Yeah? Because you have to combine, so to speak, everything you did with the outer cold atoms and combine it with cryogenics. And if you've never worked with cryogenics, this is a nightmare. So we try to do that, and we're getting very close to be there. So you basically you have to make an experiment, and you want to do experiments with superconductors and later on maybe with the qubit in there. You don't want to mess with too much light that sits in your cryostat. So we take outer cold atoms and transport them magnetically up into a cryostat through the heat sink shields, and then if you later on want to go put this in the dilution fridge, you have to do it at a cryostat which doesn't have too much of a cooling power, because regular dilution fridge wouldn't have too much of a cooling power. So we did that with a small, we built everything up with a small closed cycle fridge, which had only a cooling power of about 100 or 150 milliwatts at 4K. So in the end, after learning a lot about things, how to do that and how to engineer, currents, transport which has outside normal conducting cores and inside superconducting cores and all these other things, we can now have something like a few times thinner the atoms in there with a very long lifetime, and can cool them on a chip to a few hundred nanokelvin. And I was hoping before Christmas we were going to see a nice BC, but we don't know if we had it or not. There were some issues with the imaging and with the superconductors and eddy currents and switching up, and so I don't know. But it's getting there. It's getting there, and we have them on a chip. We can do things with the chip and something like that. So we'll not be able tomorrow to couple them to a single microwave photon, but it should be possible to couple these things to photons and learn a lot about these things. And I think anyway, these atoms are extremely good probes of local magnetic fields. They can see 10⁻⁴ flux quanta. Yeah? And so it would be also really fun to probe really what the superconductors do. And they can probe, because they can probe so small magnetic field variations, they can probe how straight the current flows. So we can see current flow variation of 10⁻⁶ radians, which we looked in normal conducting fields. But in that it would be fantastic to see, does anyone know, does the current flow straight in the superconductor? Probably not. It will probe all the defects and everything. So we'll see. There will be a lot of interesting stuff to do anyway. Yes, sir. So, knowing that this is a really tough and hard experiment, we said, maybe there are other spins we can couple. So the other spins to couple, of course, would be NV centers. So you can couple and superconductor to NV center. Now, what I say, most of it, basically, this was Johannes Meyer who did many of the experiments together with Rob Shortkoff. The original experiments with Rob Shortkoff in certainly QED joined our operation a few years ago, and so he built up many of this. Everything has to do with the superconductors. And he built it up, and he had many of this. So I think I don't have to say much about the NV Center, and we had great talks by many of the lectures here. What we're going to work with is this 2.88 gigahertz transition between the ms equals 0 and ms equals ±1 state. Yeah. Now, to get good coupling in there, and we don't have to worry about, because we do that at ultra low temperatures, so we don't have to worry about optically pumping these things. Because if we do that at 20 millikelvin, 3.88 gigahertz is something like 150 millikelvin. If you do that below 50 millikelvin, it's e⁻³ zero-curvature of another state, you can forget. Yeah, so we do more of these experiments typically with 20 millikelvin in a dilution fridge. So everything will be in ms equals 0 state from the beginning. Now, if you take that, with an atomic ensemble it was simple to calculate, because this atomic ensemble, if you have it in a 1D trap, it's very well localized. It's transversely localized to a few hundred nanometers. So you can just say, okay, what's the field there, and you take the field in the middle and then you do the calculation. Here, now we have the resonator, and on top of the resonator we put an ensemble with NVs, and that fills the whole rest of the whole rest of the hemisphere. Now, if you do that, then you have to get what you get basically an effective coupling, which is the sum of all these couplings, and you know, the further you go away, the weaker these couplings get. So it's very difficult to put in a number how many of those things give. So effectively, we couple to something like 10 to the 12 to 10 to the 13 MV spins. Yeah. The biggest contribution who couples comes, of course, from them that are very close to these gaps. Yeah. And if you have an MV concentration of something like 10 to the 6 per cubic micron, you would get effective coupling strengths in an order of about 5 megahertz. If you have 10 to the 3, you would get in an order of 160 kilohertz. So, so relative to the line width of the microwave resonators, this sounds to be fantastic. Because you know, you have, I said, a few tens of kilohertz, and you have, say, tens of megahertz, so you get a loop effect 1,000 more coupling strengths in the line width of the resonator. But tell the truth, you know, of course we did, you know, naively, you build a good resonator, put a diamond on there, and you see nothing. Yeah? Take it out, you first thought that something is broken, you do it a few times and you see nothing, then you find out, you know, maybe, you know, you look up, diamond has no loss function, you know, there should be nothing problem. Yeah? Then you make a really bad resonator, put a diamond on it, and you see it, and the bad resonator still becomes worse. So there's lots of junk on this surface apparently, which basically kills your resonator. So, and of course, if you have these, if very dense NV samples, and you don't have NV samples that are, you know, that are built by, there's one group in Japan we can make NV centers with NV ensembles with a very, very narrow homogeneous line width, but if you don't have them and make it yourself, they have many megahertz, you know, a few megahertz line widths. So in the end, it doesn't really help you to have a very good resonator. So, okay, but nevertheless, you know, there's an homogeneous line width. This comes to the, you know, because you have how you create these NVs and how you think, and there's a coupling to the nuclear spins. And so it turns out that it's nice that you know, it works out, you know. It should have been much better, but it works out. You will be able to see it. Now these resonators, and also you have to be very careful, this diamond has to be very close. If there's a gap of only 1 micron, the effective coupling goes down by a factor of 2. So our resonators, how you build them, these are these transmission lines, and you make a very small gap here and a different gap there, so you can get a resonator where you can couple, and then you put in the center of that, you put your crystal. And if you make these resonators in niobium, you know, this is one which had about a Q of about 1 million. Yeah, this is what so even though we can make them as good as we need them for the atoms, but for the NV centers it was not. So then you take your sample of NV centers, which is you know, these diamonds that glow really nicely red. You take you have your resonator here, you put them on the resonator. Yeah, you clamp them on there, and or you clamp them even stronger on there. Yeah, so they don't fall off. And then you put them in a dilution fridge. And as an atomic physicist, it's fantastic that you have now these fridges which you can just switch on and switch off, you know. This is it would be, you know, I did that as an undergraduate. I measured a deviation function from some superconductor in a dilution fridge, and it was a mess. And I told myself I would never ever work in cryogenics, you know. But in the end, you know, now you have these things where you can just push a button and it, you know, come back in the morning and it's cold. So that's really, really fantastic. And of course, there's lots of stuff you have to put in there. And there's a 20 millikelvin plate, and underneath there was a cage, the experiment, which has coils to put on magnetic fields, and in there in the center there's this circle. You have the coils here, the various types of coils, which allow you to put on magnetic fields onto the NV center, and in there you have the resonator with the things sitting there. But you have to go down there so that, and yeah. And if you do that, you find this signal. And I think that when we saw that, it was, it was amazing. It sounded amazing. Because you basically have so how do you tune that? So you tune your NV center by putting on a magnetic field. And since you have two plus and minus one state, you depending on which direction you need field, you have basically two ways of making it cross, and then you have basically if it makes spectroscopy with a resonator, and this is the resonator, and when you shift the NV through your maybe in resonance, you see very strong anti-crossing, and there's another anti-crossing. The other light comes down here. Yeah. Now there's I think there at that time we thought there's lots of interesting science questions, especially because you have this inhomogeneous broadening that you have in there. What is the reason why our Q becomes so bad when we do that, and other things. There are, we were there more or less simultaneously with other groups like the Dave Schuster and the Yale group or the Saclay group, who measured also with NV centers different types of couplings to resonators. And there's a whole series of people. By now I think you could fill up a list of probably 20 different sets of spins in solids which are coupled by microwave to the resonance. These are europium ions, for example. They're very different. These are now nanomagnets that get coupled. Now let's look at that a little bit more in detail. If you have a diamond and put them on this resonator, we have to think about, if you look at it more carefully, there are 4 different directions that the NV centers have. Now it depends on which way you put your magnetic field. This is how you shift the various types of lines, and you can see that, for instance, if your magnetic field is 3 degrees off from if your magnetic field is exactly lined, if your magnetic field would be exactly like this, then all of them would shift in the same way. But if this is a little bit off from this angle, then you see that all these different lines shifted in a different way. You go and see, if you look at that, you can see that in a very nice way, that you have, for example, if you are if you're under 45 degrees, then you see one transition, but if you're at 3 degrees, you have a very small splitting. You see many different other types of transitions that you have there. If you do the complete spectroscopy, we did that once on a part, and you see, there's many spurious other lines in there, and you see this is the NV center, this is the resonator, and you shift this one line down there, and it starts to get to the beautiful anti-crossing. And you see exactly how these lines behave for that. You can calculate that, and you see there's some kind of stress in here, and then this is how you would calculate for this specific orientation how the lines would move and everything fits together. Now you can do the following. You can see if there really is this sort of N enhancement, if this works. You can either make your magnetic field orient with just one direction, which is the 1-2 direction, or make your magnetic field orientate with a direction, with an orthogonal direction under 45 degrees. In this example here, that in example B, all 4 sub-ensembles contribute because all of them have the same Siemens splitting. Here, basically only one has a Siemens splitting, the other one doesn't have a Siemens splitting. So you have half the number of atoms, half the number of NV centers contributing to the signal here, and you find that it's exactly square root of 2, where you get the coupling frequency. Now, if you look more carefully on these lines, you find that there are some other funny lines in between here. And if you plot, more carefully what is the strength of this tone, you find that there are various types of other resonances that sit in there. Now the question was, what are these type of resonances? And it turns out these are couplings to the nuclear spin. So we did a calculation and saw that okay, there are various types of you have nuclear spins that couple, and there's various types of nuclear spin transitions that you could see. And if you take a carbon-13 spin in the first shell around the NV center, you would expect exactly this type of satellite peaks. And so you see that you can also directly couple to some of the nuclear spins. The coupling is not strong enough to really see a perfect, anti-crossing, but it's good enough to really see the coupling. And so you can basically look directly at the nuclear spins. And if, in principle, if you would have samples that are much narrower, yeah, in the inhomogeneous broadening, you could couple directly to the nuclear spins. It would be nice because you could couple directly to the nuclear spin ensemble. Yeah.
So how hard would it be in your experiments to put in a separate pulse magnetic control line that's not a part of the resonator, but you can, like build it around, maybe in a VR cavity or something, so that you could do decoupling on the spins independently from the microwave resonator? That I think even in a crappy sample you could actually access those spins.
Yeah. So you have to. The question is how much magnetic field you have to put in there, and then the problem is that the superconducting resonator only likes magnetic field that's orthogonal. If it's in any other direction, it starts to get crazy shifts and whatsoever. So, Johannes was always said, no, we don't put any other magnetic field in there because we don't know what the superconducting resonator does. Yeah. So we didn't do it up to now, but we thought about it. We first thought about if we could drive it through the resonator itself, but that doesn't really work because it has a very inhomogeneous field. Yeah. Right. So that's a problem. So it was something, and we didn't build a setup and test these things and see if we can do it. But the problem is that if you start to bring your magnetic field in very fine directions relative to the superconductor, you start screwing up your really nice resonator. And so we didn't know, when you do a measurement, so we have to first test the one thing and then the other. But I think it's a good.
It'd be fun.
Good thing. No. Yes. No. But there's some. Now, the next thing that you can do in cavity QED is not only measure things that are on resonance, but measure things that are off resonance. So you basically take your sample, and you don't measure at the resonant point, but you measure somewhere here, and at somewhere here you measure, so to speak, what you measure is then the shift of the resonator line. And the shift of the resonator line should be proportional to the coupling extension, proportional to the number of spins that are sitting in a specific set. So you can do dispersive measurements. So basically what you do is if you make your microwave tone stronger and stronger and stronger, you see that the relative shift of the cavity resonance gets stronger and stronger, meaning you put more and more, now you make two-tone spectroscopy based on the cavity. You make more and more of these atom spins to bring in a different state. And then if you do that, you can drive different specific spins, and you can measure this by measuring these cavity shifts, you can measure completely the level structure of the NV center at the specific part. And this is an example that you can basically very nicely, measure. The other thing you can do, which I thought was fun, is to measure the lifetime of the NV spins. And so you can do the following thing: you just, with very strong tone, you bring everything into make a complete mixture in there, and then you probe the cavity and see how the spins rattle down and how they cool or they fall down. And you can do either you excite the spins and then wait for some time and measure, or you can excite the spins and measure continuously. And these two curves basically lie completely on top of each other. So you can have basically really a probe on the spins that are in the ensemble without really, like they behave like they would behave in them. So some kind of a poor man's quantum demolition. I don't know, it's a non-demolition, but you can do that, and And depending on, the thing is that depending on how good these samples are, some have lifetimes that are 40 seconds, some have lifetimes that are very long, and you can see. So this is, by the way, a nuisance in that this lifetime is so long as a nuisance in these experiments, because if you really probe something hard and you create other excitations, you're going to have to wait a long time that everything is back. Yeah? Which is, if you want to do something repeatedly, you have to think about what you do, because if you do something repeatedly, you might, excite more and more of those spins, and you start to get funny effects. Now, the next thing we can try about doing this is not only probe them, but really probe them in the pulsed form. And then this is, for example, the transmission through a cavity at the resonance. So you see, we're now at the resonance point where you see now the two states that are the psi plus and the psi minus state of the dress state between the spins and the microwave photons. And basically what you do is we switch the microwave on here, and with this microwave electronics, it's beautiful because it's just watch what is happening directly on there. And you see how the system starts up. It's oscillating until it settles into one of these dephased states. And then if you switch off, you see the free induction decay coming out there. You can measure that directly. Now if you go and see that, depending on how strong your coupling is, what would you see in there? And if you have a very strong coupling, you have you see this nice curve. And if you have a very weak coupling, you just see it go up and go down. You don't have these oscillations. Now we can think about what does this inhomogeneous. This is all these things are due to that this thing doesn't oscillate long. It's due to this inhomogeneous broadening, because the lifetime is much longer. So you can get something out about inhomogeneous broadening. Then there was this idea by Klaus Møllmer, which basically said in this beautiful paper out there. They looked at spectroscopic properties of inhomogeneous broadening spin ensembles, and they predicted that if you don't have a Gaussian distribution in your spin states, that you should see different line width depending on how strong you drive your system. Now we set out exactly this. You drive it stronger and stronger, and you see that you get, if you drive very weakly, you find in the beginning you find a small line width. You find a larger line width, and if you would have a Lorentzian, you would have a Lorentzian line shape. This would be completely independent. But if you don't have a Lorentzian line shape, you would expect that driving stronger and stronger, the line width would get back. So the cavity more or less makes sure the line width smaller and smaller. When we did this very first experiment and looked at the line width directly, we saw that already that the line width was small. It didn't fit together with our inhomogeneous broadening measurements. But now this basically shows you directly that you go up and then you go down, and basically here you have a system where you in principle, if you could drive infinitely long, the line could get very small, so it goes down. You have that, you see here that.
Can I understand that in terms of regular spin locking? Is that like a T1 row line, 1/T1 row line length?
Probably, yeah. I mean, there's these beautiful spin locking experiments in the atoms and things like this, yeah. So you basically don't have a. So that was nice to play around there. This is basically, I found it funny that we can really say something about this type of states, and you can play around and take this pulse and see that what happens if you pulse your microwave field in there, and you can get to very high. You can enhance the transmission through the cavity enormously by pulsing it compared to that. This has nothing to do with it. Similar, like if you pulse it, you get if you pulse on resonant field, you get two side bands that are exactly there where your states are, and then it allows you to get a transmission through. But it's fun to play around with the things and see that this really happens. There are many other. Now, both to go on further, I think it really now relies on having much better samples. These samples are off the line some of the things, and so you have to probably go and get much better samples. And we have to understand why the resonators just die when you put this on there. There must be some dirt on the sample, and you know, whatever you do, we really treat them harshly and etch them and try to terminate them and whatever, but it's a black magic. You know, some of them are a little bit better, some of them are worse, but you know, there's some junk on this stuff on there. So, which also might be bad if you try to do, if we first wanted to fabricate all our things on the diamond directly, yeah? And then we stopped that because we said, okay, you know, we don't know what this fabrication might do, some so stupid thing that the micro is coupled so strongly to some of the defects, some of the junk that we used during the fabrication. So we basically said we first produce our things separately and put the diamond on top.
Did you ever try it though? Did you ever just go and try it?
No, we didn't. We tried it once and we had some problems with the fabrication.
So you're like,
and then they said, okay, you know, let's do this. This is fun. We can do it. And yeah, we tried it, but it was, you know, we didn't have the right process probably, and you know, we knew how to do it in some of the other substrates because people knew how to do it. And, so it's, I think you can sink a lot of time into some of this. But sometimes you have to do it, but you know. So, of course, there are many different other groups who did that, and I think there are the groups by, you know, by Rob Schmiedmayer, who did some work on there, and I think that the really nicest experiments in that sense, that went very far, are the ones by Patrice Berthet at Saclay, who really had qubits and was able to take a single photon from a qubit, put it in an NVIDIA sample and put it out again. Yeah, which I think is a very nicely heroic experiment. It's really fantastic to be able to do that. If this will ever lead to a quantum memory for an superconducting circuit, for the moment I don't think so. Then even though that there's a very recent PRX from the group in Saclay, but it did dynamical decoupling, tried to do dynamical decoupling to get the narrower line width and get the better thing, and they got to something like a 10 microseconds or something instead of a few hundred nanoseconds. But it's still, the resonated principle is still a better memory than the spins. Yeah? So, and I think it only makes sense to use that as a memory if it's 1,000 times better than the resonator. Yeah. So, okay, one has to see how these things lead to. So, you know, of course, the dream is to make some kind of a hybrid processor where everything is on there. You have, you know, you can get optical photon through atomic ensembles and get qubits and spins. But this is, you know, I think it's a dream. Yeah, and there's lots of interesting physics to be done. Now, one of those things would be, hey, you can get rid of all these problems with inhomogeneous ensemble if I can couple to a single one. And then it's much easier to do all this decoupling, and we know that these lifetimes are very long, we can put them in a nuclear spin and everything else. So there was efforts to put them into, can we really manage to couple to a single nitrogen spin? For that you have to crank up your magnetic field a lot. For that you basically need to have some kind of a transducer that produces a very strong field. So in principle you could think of the following: if I have a flux qubit and I would have one flux quanta in there, this coupling would be strong enough. But usually the flux doesn't really come out there. The flux is accessible where you can put an NV center is not that big. But in principle, you know, if you tweak all the parameters in a very nice way, that's a paper by, you know, Data Gabriel, Zoller, Lukin, and others, you can go and manage to couple to a single NV spin. Or it's a different idea by Jason Twomley, where you make a coil and wind this up a few hundred times, and then in the center, directly in the center, put your NV spin. This should also give you, if you have a perfect resonator and everything, something where you can start coupling to one or to a few of those spins. So magnetically, I think it will be very difficult. You can also think instead of an NV spin of an nanomagnet. These things are, we tried, it's tough, because the things are very, very difficult to handle. These are just the mess, yeah? And you see something signal, something you don't see the signal, it's, whatever. So it's an issue that it would be fun because they have a much more stronger magnetic moment, and it could do also lots of other interesting physics. You could do if you can couple to them. Now, there was another thing that you can enhance the coupling, enhanced coupling should be enhanced coupling by using coupling to an electric field. So you take an atom and make an atom which can make a very strong electric dipole moment, like a Rydberg atom, and then you could couple to with a pad and couple down there and couple it to another qubit, or which is also a beautiful set of experiments that I think that Hartmut Hefner tries to do in Berkeley, where you take an ion trap, and of course this ion induces small electric dipole moments into the end caps, and you want to use that to couple the motion of an ion directly to a superconducting circuit. I think both of those things are extremely challenging and it's difficult.
The trap motion of an ion usually is pretty low frequency, right? And the qubits are up at gigahertz, so...
Yeah, you have to have then, again, the sideband.
Okay.
Yeah, in the same way as you do it with the nanomechanics.
Okay, got it.
Yeah,
So upconvert.
upconvert, yeah. Many paper, it seems to working, but one has to do it.
Yeah.
And I think Hartmut is trying to do that. This type of transducers, this flux qubit was used to directly couple to NV spins, and they had we had always something like 10 to the 12, and they only needed 10 to the 7 spins because their single couplings rate was 8.8 kilohertz. So if they get their coupling a little bit better and get a qubit that is as good as the best qubits that are like some of the Exmon qubits from Martinez or something, then you could think of that maybe you can really couple to a single one. Yeah, if the qubit is long-lived enough. But you see that you can get a very strong coupling. Here was 28 megahertz for that point, and you find a strong coupling of the superconducting qubit directly to this microwave. Makes sense. Now, to enhance for this enhanced coupling, you have to go back. I think one of the earliest papers at all that looked at hybrid systems was this one from also this cooperation, Peter Haber, Peter Zoller, Lukin, and others, where they thought of, hey, what is if you take a polar molecule which has a dipole moment, and they use, say, in their tractor-acid calcium bromide, and you find, and you can go and trap these polar molecules in electric traps in the same way as you can trap neutral atoms on chip traps, and so you have to use traps that are, you have to have strong weak field seeking states, so basically you use this state and this state in here, and then you get an 11 gigahertz splitting here, and a relatively large electric dipole moment between those, so that if you're able to put this molecule to about 100 nanometers away from a resonator, yeah, then you would get a 400 kilohertz coupling. If you put it a micron away, you get a 40 kilohertz coupling. Yeah, I don't know if anybody is trying to do that. I know that people, decelerate polar molecules and trap them, and decelerate them on chips. But I don't know if somebody really just tried to put everything of this together to do that. There are various ways of, if you have that strong of a coupling, you can also do sideband cooling and do many different other things and cool the molecules directly into the trap in the end. So there's a blueprint for it, but I think it's experimentally extremely difficult to do. But that would really allow you to couple to a single one, and then this polar molecule could have, if you make it a little bit more complicated, you pick one which has good nuclear spins, and you put the thing in the nuclear spin, and then you have really something that lives for a long time. Or you enhance your coupling with Rydberg atoms, and this is something that experimentally is now being tried at ETH. Andreas Wallraff tries to do some of these experiments where the idea is that you basically make a coupling, you bring an atom to a Rydberg state, and there you have a very strong coupling between the electric dipole and the Rydberg state and the microwave, and then if you have it down, you bring it down again. In principle, you can get strong enough coupling in there to really couple to a single one. Yeah? And the problem of doing that is, first of all, nobody really knows how close the Rydberg atoms can be to the surface before they really lose their nice properties. And second of all, you need 2 photon transitions. That means you really need a lot of laser light close to the resonator, and laser light and resonators, they don't really like to live together. You create all these quasi-particles in there, and then the resonances and the coherence is just die. So there's a whole series of proposals to do that, but I think it's interesting. People try to do this first type of experiments, and Andreas saw basically that these things couple. That you have Rydberg atoms, he sent them through, and you could see a signal in the resonator. We sent lots of atoms by it, but they're not trapped or anything like that. And so that basically brings me to the end. I would probably end up with that the diagram that I showed in the beginning, that hybrid systems, an overview that there are many things you can couple together. There's, I think, one thing which is fixed. If you really want to store something, you want to store it in nuclear spins. If you really want to send something somewhere, you want to send it in a photon. Yeah. So if you want to communicate with the system around, say you have to go here. If you want to store it, you have to go here. And the rest is, and to go to photons, you either have to go to an optical cavity, or to go to this photonic band gap and optical, these permanent band gap structures. And if the nuclear spin, you're going to have to go to something like an atomic ensemble or an ensemble of AD centers or some other things. And so, you have to end up either here, and you come in here, and there's a whole slew of physics you can do there, and then mechanical resonators, I think, are one of them. Good parts to do that. And these microwave resonators are fantastic too, the optical resonators. Basically, the mediators are, these buses are 3 different resonators. Inside a mechanical bus, it's a microwave bus, so it's an optical bus. And I think there's lots of stuff to be done. And I think that, you have all these things, and I think, you really need real engineering. And I also think that real engineering quantum systems is not possible. We've seen that here in a very, very beautiful way. And it's something that's not, you don't do it, don't do overnight. That basically brings me to an end. And of course, I want to mention a few people that work with me on this, for this solid-state atom spin and photon phase interface. There was many of these, everything has to do with the microwave. There was Johannes Meyer, and he did a lot of these experiments. And he basically, advised the guy. Then there's Michael Drucke, who did many of the experiments on the NB centers, and there's some things which I didn't have time to talk about, like, and there's lots of theory collaboration on the cavities, cavity QTs, lots of collaboration with Campbell Rich, and on the side of the way of how to use them in quantum information, a lot of collaboration with Kenya Moto, Bill Munro, and Simon DeWitt from National Institute of Informatics in Japan. And all of these atom-light interface experiments, these were the experiments I did together with John-Louis Hahn when I was still in Heidelberg, and now many of the guys here are all professors in China. Yao Chen, I think they're all, both are, they're all now have their own groups in China. And there was lots of funding to be done, and there was lots of, from European Union and from Germany and from Austria. And I have to say, it's, lots of things have not been possible by some very big grants, which is an ERC, and then the British prize that it got, which is nice if it keeps you, it has you have money in the back for 5 years, which is really good. Because otherwise you cannot think about doing things which don't give you results within a year or so. So yeah, thanks a lot for listening, and I have to leave tomorrow early morning because I have to teach on Monday morning. So I would love to stay here and have more discussions. And as I said, if somebody wants afterwards to look at the comment, we can go in. If it's clear.
Thank you.
No, come on, you should not complain. We don't have the ARPA or your father.
Yeah.
Yeah, don't complain.
So, questions for Jorg?
But it's always good to complain.
Yeah.
You can never complain enough, or else that's
So I have a question. So there was it was 20 years ago probably now, a big push to try to see quantum effects in coherent quantum effects, not just molecular magnets, high spin molecules. And of course you have these superconducting circuits, you can couple them. It seems like a really obvious choice because you have a really big magnetic moment, and now I think you have the right tool to really create coherences. I don't know that they're going to have long lifetimes, but if the coupling is very strong, then I think that becomes a very interesting thing to take a look at. Is that something that...
Yes, we tried. And I would have shown you a diagram if it would have worked.
Oh, okay.
We tried, and these samples are a bitch. They are really, I mean, they are very hygroscopic, and coming from atomic physics, I have no clue how to handle that, and Johannes is working very hard. There's some collaborators from Spain who makes the samples, and we tried that, and we did a few runs, and sometimes you see something which looks interesting, but it's nothing is reproducible, nothing that's, and it probably has to do because sometimes we find that you put the sample there and you put it out there, and it's broken, it's recrystallized somewhere during the time of the way. Whatever, it has to be, in micron contact to the resonator to see something, and if something, yeah. This is exactly the motivation. When Johannes wants, this is one of his motivations, because he thought this is a really, really cool thing to do, but it's the basic, the step 0, we're working on step 0, yeah.
Thank you.
But if you know a good molecular magnet, or maybe a better type of sample, yeah, I don't know, maybe Johannes should contact you or something and find out. But it's really, it's a mess.
I'm not an expert. I just think they're neat. That's it.
I know. I think they're really, really neat, but it turned out to be much, much harder than we thought. The diamond you can press, you can put it there, it doesn't break. It just, stays there. It does that. Yeah. But the other thing is just like.
What happens to the coupling between the spins and the strip line resonator above the superconducting transition temperature?
You can get, the same thing, you can get coupling, yeah? But the resonator has a very broad line width. And then if the line width is much larger than, people did ESR coupling with really, with macroscopic resonators and macroscopic samples, and saw these. You can describe many of these things. You can describe as classical. There's 2 classical coupled oscillators, and you can see that also. It would start to become really quantum when you put a single photon in and single photon out again and things like that. Yeah. Well, everything I showed you from our experiment can be described by very weak coherent fields, classical fields. It's just classical excitation right in there now. But you see the coupling. It's strong enough. The coupling that it's a coupling that you would see from the single photon Rabi frequency thing, but the experiments itself are classical, 2 classical oscillators. Yeah? But we're happy at least we can get them to work.
Questions from the students?
In one slide, you talked about how the coupling between the resonator and the spins led to non-Markovian dynamics in the resonator. Is that a generally something that is generally seen because of the coupling to the spins?
Now I have to go. What this non-Markovian dynamics is in these calculations. I cannot really I cannot really say this is now real. It depends on the normal covering dynamics or not. I don't really know. I don't know. We'd have to talk to the guys with the theory in detail because it starts to become very, very involved. It's probably something that's interesting to really look at in details. I cannot really tell you. It's basically it's in the calculation that this dynamics is normal covariant. But if that's what we see is a proof that it's normal covariant. It's just like that it's in the calculation. I cannot really tell. I cannot tell. So don't go around and say this is a sign of normal covariant. It would be fun to do, but it's I cannot tell you. We'd have to take a bit more in theory.
Other questions? If not, join me in thanking Jorg for
Everybody for the other.
maybe the other